I'm here with Steve Mould because I have made a jigsaw puzzle I'm very proud of. I'm going to get Steve to try it out. It's on the back of the board, currently solved. So Steve, if you could look away for 1 second. Yep. Everyone at home, you can see that it's a picture of
a coffee mug.
Now, don't tell Steve what it is. I'm going to take the pieces. Oh, it's magnetic, so they stick on the board. So I'm going to break it up into a shuffled pattern. Okay, so Steve.
Yes.
This is the jigsaw puzzle. You can see it now. There it is. You have to put these pieces back together into a picture of a thing that we already know what it is. Okay. So off you go. And I'm very proud of this. If you notice some of the pieces look like they're very jagged at low resolution, that's because it was a complex process making it. And we'll explain exactly what went into it and why it looks like a kind of a weird abstract art version of the thing that it is. But first of all, we'll just give Steve a moment to try and solve it.
Finished.
Oh, hey, all right.
Shall I do a big reveal?
Yeah, well, I know what it looks like. So, what?
This video is supported by Jane Street and their fantastic internships, which are open to applications now. And I've got an announcement relating to me and the Hong Kong internships. That's at the end of the video.
Isn't that donutty? Absolutely incredible. Okay, so in post, we will show the before, which was very much a coffee mug.
Are you doing that maths thing where you say, oh, it's a coffee mug?
It's a donut.
Yeah, because you look at a donut and you go, it's a mug, ha ha.
Okay, so obviously, Steve, we both knew both solutions before. Yeah, because this has taken a very long time to make it work. And they're exactly the same pieces. There's no trickery between them. And we have an animation showing exactly these pieces can be rearranged from a mug into a donut. I am disproportionately proud of the fact that this works.
And while it may not look like it in this animation, not all of the knobbly in and out bits of the jigsaw puzzle are the same. There are different types. I can guarantee this only fits together in 2 arrangements. And we'll go into the mathematics of that in a moment. But first, this all started when Steve showed me something called a diffusion illusion.
So I had this twisty puzzle thing, and I wanted to see if you could come up with an image you could put on there, and it would make sense in both orientations of this twisty squares thing. And after I mentioned it in a video, I got a lot of people trying to create images that would work, and then I got an email about using generative art, so AI generative art, to create an image that would work in both orientations. Yeah. So that's what my video is about. It's twisty square illusions that work using AI, but there's other things that use transparencies and stuff like that.
That video is out now on Steve's channel. I'll link to it below, but Steve has brought some to show us.
Weeping Angels.
Weeping Angels? Yep.
From Doctor Who.
No.
Yoda. Is it Baby Yoda or is it Yoda?
Regular Yoda.
I think it's regular Yoda.
Okay, yeah.
Do you know what? I actually have a donut as well.
No.
Yeah. And you'll be very pleased to see
it becomes
an ice cream.
But these are they're just incredible.
Yeah, it works incredibly well, doesn't it? Well, this is a good one as well. Oh my gosh. This is a good one. It's a winter scene. And then a bit falls off, but it becomes
most of. It's got a real homemade vibe. I love it.
Yeah. Oh, look,
I thought mine was going to look a bit unprofessional, given it's like cut out bits of card with magnets on the back, but no.
Yeah, well,
how does this work, Steve?
Yeah.
Now, before we get to ambiguous images, we just understand how does AI make. Like, how do you give it text and it turns that into a picture of something?
Yeah,
out of nowhere.
Text to image generation. So it's this denoising thing.
Oh.
And it's kind of surprising that it works at all, but you train a model to figure out how to remove noise from an image.
Right.
Noise being like, the grain you might see on it. And then you just add more and more noise progressively until it's just pure noise. And then you say to the model, get rid of that.
Oh, so you just give it absolute noise and say, hey, this is actually a picture of a donut.
Yes.
Get rid of that noise.
Yeah.
But there's no donut.
There's no donut. So what happens is, actually, it's not great if you just say, remove all the noise. The result that you get when you try to remove all the noise in one go, is it's a blurry blob.
Right.
And so you do that step several times. You add most of the noise back, and then you try to remove that.
Try again.
You add a bit less of the noise back, remove again. Each time adding less and less of the noise back, and each time you get a sharper and sharper image of a donut, right?
Amazing.
But you don't care about that stuff when you generate an image using Stable Diffusion or whatever. You just put the prompt in and you get the image. But what you can do, because it's open source, you can interrogate the code, right? You can say, halt at this point, right? Instead of just going straight to the last image, show me the first thing that you came up with. Right?
Yep.
That's going to be the blurry thing that's kind of like a donut, right? And then you say, okay, for the next step, actually, I don't want a donut anymore. And actually, in fact, just rearrange all these pieces. I want that to be a mug.
Oh, okay.
Right.
Now do that.
Now do that. And then you say, actually, do you know
sorry.
what? No,
I don't know what I was talking about.
actually, put them back the way they were. I want
donut,
that to be a
please.
donut.
Yeah.
Actually, just back and forth.
Oh, actually, on second thoughts.
Yeah.
Mug.
Yeah. So the whole time, there's like these little baby steps where you're approaching a mug, but you're also approaching a donut at the same time with the rearranged pieces.
And a little bit of selection bias, because you do that a bunch, and then you pick the ones that look good.
Yeah, so maybe you do this and actually you get a lot of rubbish results.
I can actually say we did, with the same jigsaw pieces, lots of mug donut combos. This was my favorite. But here's a bunch of the other ones.
All of these images are based on exactly the same underlying jigsaw structure that I discovered. We just had to pick our favorite one to actually print on it. Let me know if you would have picked a different one.
Here's the thing I don't understand though. No.
Yeah.
We need to talk about this jigsaw though.
Yes, I
Like
would love
when
to.
you do a jigsaw puzzle and you try and put an outie in an innie.
Technical phrase, yeah.
Sometimes the shapes don't match.
Correct, yeah.
And that's by design.
Yep.
And actually, the only time the innie will match the outie is if those two pieces are supposed to be together, right? But this has two solutions,
Yes.
which means that you somehow have duplicate pairings of like
Correct.
innies and outie shapes.
Yes.
Okay.
So this is a 5x5 grid.
Yeah.
And if people have a quick think about it, you can realize there are 40 internal edges.
Right.
Which means if this was like a handmade jigsaw puzzle, there'd be 40 unique ins and 40 unique outs. This, however, has far fewer distinct types and they appear multiple times. There are actually 7 different in and out combos and they all appear 5 or 6 times each.
Oh, because so in my mind, the optimum thing was each pairing just needs to appear exactly twice.
That's a good point.
Yeah.
But that's a terrible way to do it. So when you first showed me this idea, and I thought, I wonder if there's a jigsaw puzzle with 2 solutions. I was like, well, hang on, it must exist. Well, probably exists. Because if these are all different, 1 solution only. But then imagine a jigsaw puzzle where these are all the same. You could put any piece anywhere. If you had like systematic, obviously you got the edges,
Yeah.
but if all of these were always in, out, out in the same orientation for every single piece,
Yeah.
the pieces are fungible. You could
Yeah.
put them anywhere.
And
that
that's
would-
too many solutions, that's boring.
It would be an outrageous number of solutions.
Yeah.
And so I was like, oh, okay. In the extreme, if they're all the same, you've got an outrageous number of ways you can put it together.
Yeah.
And at the other end, you've only got one way.
Yeah.
I know it's not strictly guaranteed, but it feels like in the middle, there should be a
Yeah.
bunch with 2. So what I did was,
I can hear it coming.
would you believe I knocked together some terrible Python code?
Yeah.
And I explored what happens if you vary the number of different types of edges in a jigsaw puzzle.
Right.
Would you like to see some results?
Yes, please.
Here they come. So the way I thought about this was, if I had a random 5x5 jigsaw, except I can choose how many different types of ins and outs, what's the average number of solutions it would have?
Right.
So if every jigsaw only ever has 1 solution, then on average, you make one at random that's just got that 1 solution you start with, there's no more.
Yeah.
If very occasionally there'll be a second solution, or maybe a third solution, then on average you'd have like 1.0000 something solutions on average. And the bigger that number is, it gives you an indication of how many solutions you get. So this is a plot. Let me talk you through this.
Yeah.
On the bottom here, this is the number of different types of edge.
Right.
So this is a 5x5 with 6 different types of ins and 6 types of outs that match.
Okay, yeah. So the maximum is like however many.
Yeah, it would be
edges
40.
40, and then the minimum is.
1.
Yeah.
So I didn't go all the way down to the minimum because as you can see, this is an exponential graph that goes flying up. Actually, I didn't even think I was going to get 6 because I ran the code to do 1 million of each.
Yeah.
And then the million of 6, because I started at 18 and worked my way down, was taking so long. I just made the graph from 7 to 18 and moved on with my life.
Yeah.
But then the next day I happened to look at my laptop and I left the code running and it had the results for 6.
Oh, nice.
I was like, oh great, in go 6.
Yes, because the fewer different connections there are, the more ways there are for arranging it in terms of your code.
It's got to explore all the solutions. We'll get to that in a moment.
Yeah.
It's not good. So in the end, I decided to go for 7, which is why if you ignore the outside edge, this has 7 different types of internal knobbly bits.
Right.
I then did a bar chart just for 7 to see what kind of a distribution I was dealing with.
Right.
And the bar chart looks like this.
So vast majority one solution.
Yeah, 96.0306% of the time.
Yeah.
You got one solution, nothing else. Down here is the golden zone. This is what I want. 3.7% of the time, which is not bad.
Yeah.
Like if a computer's just generating these at a phenomenal rate, 3.7% of them being what you're after. But I can say, for the cases where you get lots of solutions, they're all going to be pretty similar.
Just like switching two things or...
Exactly.
Yeah.
So that's when I realized, hang on, I've got an issue here. I want to have a jigsaw puzzle that's got 2 different solutions, but I want them to be as different as possible.
Yeah.
So I then had to measure the difference between the solutions and then try to get the maximum difference between them.
Yeah.
This one, there are only 2 joins that are the same in both solutions.
Right.
I then did find one that only had one that was the same because I foolishly left my code running, but I was already too deep in committed to this one. We'd done too much work finding the image.
Right.
I wasn't about to jump ship to the other one.
Okay, yeah.
But technically there is a better one out
Okay.
there. Yeah.
So in summary, the fewer duplicate edge types, the better.
Correct.
Because it makes it a more interesting puzzle, a less frustrating puzzle where 2 pieces might fit together, but actually that's not a solution for either of the 2.
Correct. In a perfect world, I would have had 20 different ones, each in there twice. Very pleasing.
Yeah, but that's very hard to find.
At least with my code.
So let's make it easier to find using public code review. It's worked for you so well in the past. I just think, and then you might find this beautiful jigsaw puzzle.
Yes, okay, fine.
Okay.
Now, I know you're going to suggest my code could be better, but let me explain how I did it.
Okay.
And then everyone can do it better than me.
Sounds good.
So, the first thing I needed was some code that could just solve a jigsaw puzzle.
Yes.
So a bit like Stable Diffusion, you could argue being able to denoise an image is a useful process in its own right.
Yeah.
I just needed the process which was take some jigsaw pieces and solve that puzzle.
I wrote a program I called the Jig Checker, into which you can put a partially solved jigsaw, all the remaining pieces, and then it will start checking what fits. It's not called Jig Solver. It's not trying to solve the jigsaw puzzle. It just picks one spot, the next spot along as you go from left to right, top to bottom, and then it starts seeing which of the remaining pieces fit in that spot. Eventually, one of them will, and you might think, oh, now it'll start checking the next spot over. No! That's what a jig solver would do. The jig checker just takes a complete copy of everything done so far and puts that into a new instance of itself. And it's the new one that checks the next spot along. The first jig checker will keep checking that same spot until it's checked every single piece. Its job now complete, it will simply fade from reality, and the new one will start checking the new spot. Well, I say start checking, it doesn't necessarily happen in this exact order in the processor. The point is just it's recursive code, and against my better judgment, here is my actual Python code. You can see at the top, I've defined something called the jig checker. You tell it how big the jigsaw puzzle is, you give it all the pieces that are already solved, they've been placed, all the pieces remaining, and something called SPUD. I'll get to that in a moment. And then the code goes through, works out what the requirements are, checks which pieces fit, like rotates them to make sure it's checked all the orientations. If one of them fits, you can see here it takes the copy of all the placed pieces so far, adds in the new one that fits, copies the remaining one, removes the one that we've now put into the solution, and then just puts that into JigChecker. It just passes it into itself. I love recursive programming. I should explain SPUD though. It's a ridiculous name. I don't know why I use it. I think previously I had like a hot potato being passed around. That is a global list that exists separate from all the recursive jig checking going on. And that means if any one instance of JigChecker solves the very last piece of the puzzle, that solution can be put into SPUD. And that means I can just run all the JigCheckers until they're eventually finished, and then I look at SPUD, this global folder, to see how many solutions it has. And the vast majority of the time it will come back with a single solution, but every now and then another solution will be in there as well. And that is what I'm looking for. And given I've now shown you some of my terrible Python code, I may as well show Steve as well.
You know, against my better judgment, I'm going to show you some of the code. I don't know why I'm doing this. So
I was going to say I won't understand it, but it's Python code.
It's Python code. You can read it. Yeah, it's prose.
Okay.
So you know what? Just so you get a sense of what I was doing, I've written a bunch of other stuff elsewhere, which is JigChecker is the process that solves a jigsaw puzzle and gives you back all the solutions.
Right.
And there's some other code. It can rotate it. It can generate a jigsaw. It can name a jigsaw. And it can mutate a jigsaw. So what I did was, first of all, the code starts randomly generating jigsaws, looks at the ones that come back with two solutions, checks how distinct they are, and calculates what percentage of edges have changed. And I've set here a threshold to start is 25%. So it does that at random until it finds one with more than a quarter of the edges are different. And then it spits that. So this is it finding that here. It then spits it into this code that generates, what have I got it set to? Some number of children. Let's have a look here. 6,000. It mutates it 6,000 different ways. And it can vary the number of mutations. And it looks at all 6,000 offspring, finds the one with the best improvement in how different the solutions are, makes that the new parent.
That has babies.
6,000 babies. Finds the one of those that's the most different. Then 6,000 babies, and the babies all have, I did a bunch of tests, 6 mutations, so it does 6 swaps at random, is the best way to maximize the improvement. But then you got to hone in on the solution. So if it can't improve it anymore with 6, it then does 5 mutations, and then 4 mutations, and then 2, and then all the way down to 1. And then it's got some grand one it's evolved towards, and then it spits that out. And then starts again. And then spits it out, and then starts again. Spits it out. So I did a bunch of tests, because if you have more children, it evolves better, but it takes longer per test. Whereas if you have fewer children, you can bang through the tests, but each one's not as good. I would assign ins and outs to one solution, and then I would adjust them as I was then building it into the second solution. You know what? I will show on screen what this looked like when it came out of my code, because all it is a list of lists, where each list is just, it starts in the west and is 4 numbers. So this one from memory is like 0012 or something else over here. And then that's it. It just boom, spits them all out.
That's cool.
Okay, maths. But the dream, the absolute ideal, would be for some jigsaw ratio, I did all squares, could be anything, to have 2 of every type of in and out match, and have 2 solutions with no repeated matches in a non-trivial way, just in case there's some trivial way where you can just like shunt everything. If you're going to improve on what I've done, write your code from scratch. I wouldn't use what I've done to do it. You might be wondering 2 things now, which are actually the same thing, which is, how on earth do you actually take this solution I've found for jigsaw puzzles and put it into the AI image generator? Like, how do I tell it where the knobbly bits are? And you might be wondering why, if you have a close look at these pieces, they're clearly quite low resolution. They're like quite jagged around. Yeah.
The ins and outs are quite pixelated.
Camera person Alex and producer Nicole spent a very long time with scalpels cutting out actual pixels. So well done them. That's an artifact of how we had to run the code. And by we, you put me in touch with the fantastic Ryan.
Yes.
And Xiang.
Yeah.
And they explained to me how you can actually enter your two different states, whatever they may be, into the code and get your ambiguous image.
Meet Ryan Burgett, the person who first came up with diffusion illusions while doing their PhD, which involved computer vision and generative AI.
The way that diffusion models work is they progressively refine images. So if you can progressively refine an image in two different ways at the same time, then you can create two different image targets at the same time. And it occurred to me that flipping something upside down works really nicely because your vision system, as a human, isn't used to seeing things upside down. So you can hide some extra information there.
This is Ryan's Diffusion Illusion website, which has all sorts of phenomenal illusions on it. I will link to this in the description below. We have the overlay ones here, and some of my favorites are these slidey ones, where you move all the images on top of each other, which I'm doing right now, and they give you a new image. What could it possibly be? Oh, for the love of. Anyway, do check it out. There's some really cool stuff on here. But now the point is, how are we going to make my jigsaw puzzle illusion?
So a UV map is a way of mapping a texture onto an object where we have two values, U and V, which are image coordinates, and each point on a surface of a mesh will have a different UV coordinate, and we can actually represent those UV coordinates with red and green, respectively, and then use the red and green values of different images to assign where the texture pixels go. And in our case, we have two UV images of movement within a UV map. One is the basic UV map, which is just black on the corner and then yellow on the other corner with green in one corner and red in the other, which is the identity UV map where nothing changes. And then we have the second UV map, in our case, which is where we rearrange all the puzzle pieces. And in that UV map, it basically gives a one-to-one correspondence of where each pixel moves, a dense correspondence to transport pixels from the unwarped image to the new warped image, which is now the moved puzzle pieces.
Here's the unwarped UV map that Ryan sent me, except now it's 255 in each direction. That's because my puzzle is on a 5x5 grid, so it has to be a multiple of 5. Each of these boxes are 51 by 51 pixels. In fact, here's the actual low-res version of my jigsaw puzzle I did, and you can just see how chunky these things are. But while there are other ways to get higher resolution UV maps, we just went with the 255 by 255, and it meant I could then select a piece. So for example, this one here, and if you zoom in, you can see I've turned off anti-aliasing and the like, but still it ended up not being completely perfect, which is a little bit annoying. But the point is, I could then select that from the UV map, so we're going to cut it out there. And I know, because I got my code to spit out destinations, I know if I put that in here now, I've got to rotate it one to the side, and that one ends up going exactly there. And so I went through, there it is, pixel by pixel, moved it around, and actually here you can see these are the only two places where two pieces are still contacting their original neighbors. Everything else has shifted around, and my eventual result wasn't perfect, but it was good enough for us to get a first pass. I'll do it a bit differently next time.
I will explain how you can get a copy of this if you want to play with it yourself, and do let me know if you write better code. But first we need to thank the sponsor of this video, which is Jane Street.
Jane Street.
Jane Street are financial.
I'm sponsored by Jane Street.
Well, your video about
mine.
Jane, really?
Yeah.
Their internships, their phenomenal internship program that you can apply to now.
Yeah.
That's incredible.
With a particular focus on Hong Kong.
How about that?
Yes, Jane Street's incredibly generous paid internships for students graduating in the 2026-2027 academic year are now open. They have offices in New York, London, and, as Steve mentioned, in Hong Kong. So if you want an internship in things like quantitative trading, software engineering, research, and more, you can apply for any of the internships at any of the offices. You don't need a background in finance to be part of the program. A lot of Jane Streeters were in the same position as you before applying, and they learnt it all on their internship or on the job. So I highly recommend either you apply if it applies to you, or you tell someone else about it, because it's a fantastic opportunity. They pay all your expenses to get where your internship is, including Hong Kong. And speaking of Hong Kong, extra perk for that one.
And if you do end up on the Jane Street Hong Kong internship, you will get to meet me. I've now booked a trip to Hong Kong. I'm on my way to Australia in June 2025. So if you're there as an intern, I'm going to drop by the office, give a talk. I've done it twice before. I'm very much looking forward to it. You've not been to the Hong Kong office?
Not yet.
Although we have done a talk together at the London Jane Street office.
Correct.
Yeah, Jane Street. They're good people. Check out the link below. That's it for the video. I am going to make this available. I will put 2 documents linked below in the description. One is this in like the solved state, so you can still cut it out and try and solve it yourself. And I'll do one where it's all jumbled up. So if you want the challenge, get the downloaded one, print them out, cut them out. Good luck. And huge thanks to Steve Moll for being here.
I think you should also put the vector image of all the cut lines, so if anyone's got a laser cutter, they could laser cut pieces maybe.
That file doesn't exist. Okay. Because I manually move the pixels around by hand in Photoshop. I'm not ready to talk about it.
Well, thanks for having me.
Thanks for watching the video. Check out Steve's channel.
It's just fun to think about how it could possibly work, and it's interesting, like the glaze here.
Yeah.
The glint could also be a background if it needed to be. You know what I mean?
I love playing spot the handle.
Oh yeah.
Because somewhere in here is the handle from the other solution. I'm pretty sure that's it there, and that fills it in.
Oh, yeah.